Good afternoon, dear students. We are discussing about architecture of commercial devices, that is the devices which are available in the market for programmable logic devices. Okay, so in that we have discussed till about what are the different types of programmable logic devices, and after that now we are discussing about what is CPLD, then what are the commercially available CPLD that we are discussing. So in the yesterday's lecture, we discussed about uh, Max 7000 series. That is a Altera Max 7000 series. About that we discussed in the yesterday's lecture. Okay. Now in today's lecture, we are going to discuss about one more type of CPLD which is available. That is Xilinx XC9500 series. Okay, so it is another series that is available in the market. That is a complex programmable logic device. So we are going to discuss about that series in today's session. Okay, so I'll share my screen. So in today's session, as I said, we are going to discuss one more type of CPLD, that is a XC9500 series. Okay, so it is a family of different ICs. Okay, so 9536 and all other ICs that we are going to discuss later, which are the ICs. So, but this is a combinedly one family which we call it as a XC9500. Let us first see what are the features of this CPLD. Okay, so the XC9500 CPLD, that family provides advanced in-system programming. Now, what is mean by in-system programming? That means whenever we want to program any chip, okay, so we need to configure that chip so that we can program it. Okay, but if we have certain facility in such a way that if we can program that chip whenever it is on a board itself. Okay, that means it's every chip that comes with its certain board. Okay, so if we can program it on that chip only, then that is advantageous because it makes that system easier to program. Okay? Then we call that programming as a in-system programming. That means there that chip is on its board itself and we are programming for that. Okay? And then it has test capabilities for high performance and general purpose logic integration. Okay? So this is the most important feature of XC9500, that it is having a advanced in system programming and also it has test capabilities with a high performance. Then all the devices that are in system programmable for minimum of 10,000 program or erase cycles. Okay, so that means whatever programming that we can do for each of these devices, that can have minimum 10,000 programming cycle or erasing cycle. If we want to erase whatever we want have programmed, or if we want to program newly for that device, then minimum we can have 10,000 program cycles. Okay? Then it uses extensive IEEE 1149.1 JTAG boundary scan support. Okay, which is also included on all family members. So whatever are the members in that family, XC9500 family, it's IEEE 1149.1 JTAG boundary scan support is provided. Okay, now this one IEEE 1149.1 that is a IEEE standard. Okay, for a JTAG, that is a Joint Test Action Group. Okay, so here, as you know, that boundary scan, that is the one of the testing methodology for sequential circuits, or it can be used for the combinational circuit also. So this standard is supported by or each of the member in a Xilinx XC9500 family. Okay, so because of that, it makes this system as a cost effective, because it has this testing methodology where we can use a JTAG, that is a Joint Test Action Group, the IEEE standard, and strengthens the quality of your product. Okay, so the test programs that to be generated before it can be used. So because of that, whatever is your design that you can verify earlier, before it is actually programmed, okay, or we are programming it, but before it is finalized. Okay, so before that you can test whatever is your design, and then because of that it becomes cost effective. Then it has low density of the XC9500 devices that ranges from 800 to over 6400 usable gates. Okay, so that means logic gate density, that logic gates that are available on this XC95 devices, that are near about 800 to 6400 usable gates. Also, there are 36 to 288 registers, okay, on this board. Then multiple package options and associated IO capacity, that is another feature of this Xilinx CPLD XC95 family, 9500 family. Then this family is fully pin compatible, that is allowing easy design migration across multiple density options in a given package footprint. So here you can easily migrate your design, and you can easily erase and program this um, IC. So these are the summarized features of XC9500 family. That is the first feature, that is it has high performance. So pin-to-pin delay, that is of a 5 nanosecond at all pins of XC9500 device. Okay. Then it has, as I said earlier, it has large density range, that is a 36 to 288 registers. That means actually these are the microcells that are available with nearly about 800 to 6400 usable gates. Okay, so again another feature, that is a 5-volt in system programmable device, that is it is. So IO blocks or other blocks that requires 5-volt supply. Okay, and as it is, I said, it is a in system programmable. That means you can program it whenever it is available on a chip itself. Okay, that means still we are having it on a board itself. Once you program it, once you test it, then you can detach from its board and you can use it in your application. But you can program it, still it is attached on a board. So it has nearly about 10,000 program or erase cycles. Then uh, it is enhanced pin locking architecture. Also, it is a flexible 36B 18 function block. Then it has 90 product terms, which drives 18 macro cells within the functional block, and it has global and product term clocks. Then output enables set and reset signals. So these are the extra signals that are available. Then slew rate control on individual outputs. So that is also, as you know that slew rate, that is a very important concept, and that control is available on individual outputs. Then it is a user programmable ground pin compatibility, and it is an advanced CMOS 5-volt fast flash technology. So that uses this technology. So these are the different features of XC95 device family. Okay. So now let us discuss about what are the actually blocks in this family. Okay. So each of this XC9500 device, it is a subsystem which consists of multiple function blocks. Okay. Then it has IO blocks, that is also called as a IOB, and uh, it these IOBs and function blocks, these are fully interconnected by fast connect switch matrix. Okay, so that means these three are the most important parts of this XC9500 series. One is the function block, that is a FB, IO block, that is a IOB, and fast connect switch matrix. Okay, so this IOB that provides buffering from device inputs and outputs. Okay, and each of FB that provides programmable logic capability with 36 inputs and 18 outputs. And the fast connect switch matrix, which is available on the board, that connects all FB outputs and input signals to the FB inputs. Okay. For each of the FB, that is a functional block, 12 to 18 outputs and associated output enabled signals that drives the directly to the IOD. So here we have, depending on whatever is the package pin count. So each of this F functional block that has 12 to 18 outputs and that are associated with output enable signal also. And this directly drive the IO blocks. Okay. So this is the actual architecture of this XC9500 device family. Okay. So here you can see that this is the IO blocks that are present. Then this is the fast connect switch matrix, and these are the different functional blocks that are available on this in this chip. Okay. Now there are certain global clocks, then global set or reset, global tri-states. These are the different signals that are available, and these are the input and IO pins that are available. Then besides this, it has a JTAG port which is for the testing purpose that is available. So there is a JTAG controller and in-system programming controller that is also available here. So as we discussed earlier, this XC9500 device family, it has 5-volt in-system programmable CPLDs. It is having 5 nanosecond pin-to-pin delay, and it has 36 to 288 macro cells and nearly about 6400 gates. Okay. So this is the industry's best pin locking architecture. Okay. Then there are nearly about 10,000 program or erase cycles, so it can work with these many cycles, and it has complete IEEE 1149.1 JTAG capability. So these are the different features, and as I said again, I will repeat this, that it has a IO blocks, then functional blocks. So multiple functional blocks that are available. Here you can see there are 4 function blocks that are available, and it is having a IO block, that is the IOB, then fast switch matrix. Okay, so it is available. So these are the major parts in this device. Okay, now this IOB that provides buffering of the device inputs and outputs. So whatever are the inputs and outputs of this device that are buffered using this IO block, okay, or that are connected to another blocks using this IO block. Okay. Then here this FB, it has each of this FB that has a programmable logic capability. So that means here each of this FB that has the microcells, and there you can program it according to the functioning required. Okay, and it has 36 inputs and 18 outputs. So each of this functional block, it has 36 inputs and then it has 18 outputs. And then fast connect switch matrix, it connects all the outputs of FB and input signals to the FB inputs. Okay, so that are connected using this fast connect switch matrix. So switching action that can be done using this fast connect switch matrix. Okay, so this is about the architecture of this XC9500 device. Okay, so now let us see each of the block here separately. Okay, so first of all we will consider a functional block. So now, as I said earlier, so each of this uh, here on this XC9500 family, there are multiple functional blocks that are available, and each of this functional block that is comprised of 18 independent macrocells. Okay, so that means there are 18 macrocells that are available in this functional block, and each of this is capable of combinational or registered function. So you can have a combinational functional that is available, or you can sequential function that also it can be programmed using this functional block. Okay, so this functional block also receives a global clock, output enable, and set reset signals. So each of this functional block that will have the inputs like a global clock. So whatever is the clock which is globally available on this device, that is also available at a functional block, then output enable. At the same time, set and reset signals that are also available there. The FB generates 18 outputs that drive the fast connect switch matrix. These 18 outputs and their corresponding output enables signals also drive the IoT. Okay, so here I'll switch to this functional block diagram. So here you can see that this is the diagram for the functional block. So each of this functional block, it has 18 macro cells. Okay, so here these are the 18 macro cells that are available on this functional blocks, and using these macro cells, actually what is macro cells? Macro cells, that is a design approach to manufacture ASIC. Okay, so it is nothing but uses OR gates, but it also uses certain higher level logic functions such as flip flops, then ALU. So similar, such a type of functions that are available there, and these logic functions, so that means whatever logic functions are available, that are simply placed at regular predefined positions and then manufactured as a wafer. So all these functions that are manufactured as a wafer, that means as a IC that are manufactured. Okay. So here this, as I said, this functional block of XC9500 series, it has 18 macrocells, and then this functional block that receives global clocks, then global tri-state, as well as set and reset signals. Okay, then here these FV that generates 18 outputs, so that means each of this macro cell that will generate output. So 18 outputs, and that drives the, here you can see that drives to the fast connect matrix. Okay, switch matrix. So whatever is that matrix, so that will be driven by this outputs. Okay, and these 18 outputs and their corresponding output enable signal, so that also drive IoT. So here you can see that whatever are the outputs from these macro cells or from these functional cells, that also drives the IOS block. Okay. Then logic within the functional block that is implemented using sum of product representation. So here we are having a product terms which are represented in terms of sum. Okay, so that means final function is nothing but a sum of product representation. And there are 36 inputs that provides 72 outputs. Okay, so that may be in terms of true or complement signal. That means it is a either, if we are considering A as an input, then it may be A or A bar. So there are, with the 36 inputs, we are getting 72 true or complement signals into the programmable AND array. So here this are having 36 inputs. So here we are getting 72 outputs, which may be in the form of complement or true signal. Okay, and this forms 90 product terms. Okay, so this forms 90 product terms, and then out of this 90 product terms, it can be allocated to any of the macrocells. Okay, so each of this macrocell, this product terms that are allocated through this product term allocator. Okay, so that means with this 36 inputs, we are getting we are having 72 inputs that are in the form of true or in a complement form as an input to this AND array. Okay, and this AND array generates 90 product terms. Okay, though as we are having 36 inputs, that means 2 raised to 36 combinations of the inputs that may be available, but out of that only 90 selective outputs that will be available at the output of this AND array. Okay? And then with this product term allocator, the out of these 90 product terms, one product term will be allocated to these 18 macro cells. Okay, so this is the functional block that is available in a XC9500 CPLD. Okay, then
Excuse me, ma'am.
yes,
मॅम आधीच्या स्लाइड घ्या ना 1 मिनिट.
yes, this one.
हां मॅम. मॅम जेव्हा आपण नाही ती डायग्राम मध्ये
Then this one or this.
हां ही मॅम.
Okay, this is the functional block of XC9500.
ओके मॅम. मॅम आपण जेव्हा व्हॅल्यू सिलेक्ट करतो तेव्हा मग ते एक आणि अँड अरे थ्रू आपण प्रोडक्ट टर्म अलोकेटरला घेतो आणि तिथून आपण एका मायक्रोसेलला देतो का सगळ्यांना एकदमच अलोकेट
एका
करतो?
microcell that is allocated to each of these macros. Any number of these product terms that can be allocated to macrocells. Okay. So depending on the functionality that you require, so any number of product terms from these 90 product terms that can be allocated to macrocells. So each macrocell can have any number of product terms, but then again there are when we are going to discuss about macrocells, that picture will get more clear. So how we are going to give the inputs. Okay, so इथे आपण काय करणार आहे, ज्या काही 90 प्रोडक्ट टर्म्स असणार आहेत त्यातले कितीही आपण या प्रत्येक मायक्रोसेलला ऍज अ इनपुट म्हणून देऊ शकतो.
ओके मॅम.
So each of this functional block that supports local feedback path. Okay, except 9536 IC. Okay, it does not support a feedback path, but others support local feedback path that allow any number of functional block outputs to drive its own programmable AND array without going outside the functional block. So whatever is the programmable AND array that is available on that functional block. So here you can see in this picture. Here this is the functional block of the this is the programmable AND array. Sorry, of this functional block. Then this is the product term allocator and these are the macro cells. Okay. So there is a local feedback that is available in a this series where it drives the FB output. Okay, so that can be used there, and these paths are used for creating very fast counters and state machines, which all state registers, where all state registers are within the same functional block. So that is the one most important feature of this XE9500 series, that we can have a local feedback path, so that programming that becomes more vast, okay, and that becomes easier, so that you can get more functionality in a IC. Now, here, when we are going for the macro cells which is present in this functional block, so each of this XE9500 macro cell that may be individually configured for a combinational or a registered function. Okay, so there are 5 direct product terms from the AND array that are available for use as a primary data input. Okay, so as I said earlier, that we can give any number of product terms. So, but out of that, 5 direct product terms that from the AND array that are available for use as a primary data inputs to the OR and XOR gates in the macro cells to implement combinatorial functions or as a control inputs, including clock, then set reset and output enable. The product term allocator associated with each macro cell selects how the 5 direct terms that are used. Okay, so now here we can give, as I said earlier, that we can give any number of product terms out of that 90, but out of that 90, only 5 direct product terms can be given as a input to the OR gates that are present in that macro cell. Okay, and this product term allocator that decides which product terms or how that 5 direct terms are used. Okay, so the macro cell registers that can be configured as a D type or T type flip flop, or it may be bypassed for combinatorial operation. So in the combinational circuits, okay, actually we don't need flip flops. So in that case, this can be bypassed. These flip flops can be bypassed, and we can just have a logic circuits there. Okay. So each register that supports both asynchronous set and reset operations during power up, all user registers are initialized to the user defined preload state. Okay. So default to 0 if unspecified. So that means all the states that will be as a 0 if it is not specified. Otherwise, if it is while programming, if it is specified, then it will go to that state. So this is the diagram for macro cell of XE950. Okay, so whatever is the macro cell that is available in the functional block of XE9500 that is shown over here. Here you can see that actually this one is the macro cell. So here this is the product term allocator. So that gives input to this OR gates. Okay, and there is also XOR gate that is available in this macro cell, and then this output of this XOR that is connected to the D or T flip flop. So actually this is the macro cell which is used for the higher logic functioning. Okay, so here you can have just a combinational circuitry. Okay, whenever you have just combinational circuitry, you can bypass this flip flop and just you can go directly to the multiplexer, which will select the whether output of this is to be connected to the fast connect switch matrix or it is going to the IO blocks. Okay, so that could be selected using this multiplexer. So here you can see that this multiplexers in the macro cell that uses global set or reset signal, as well as it uses global clock also. Okay. So this is the macro cell that is present in the functional block of XC9500. Okay. So remember that there are 18 macro cells in a XC9500 um, device. Then here let us discuss about the global signals that are available in the this device. Okay, so this all this global control signals that are available to each of this individual microcell. So globe, that is a clock, then set reset and output enable signals. So here you can see that this global set reset signal that is connected to this multiplexers. Okay, so where we have the product term set. Okay, then product term clock as well as product term reset. So this macrocell register, that clock that originates from either of three global clocks or a product term clock. So here from this this clock will get generated. Okay, that is a global clock 1, 2 and 3. So there are three global clocks out of that, or this is a product term clock. From this clock of this macrocell that will be generated, and both true and complement polarities of GCK pin that can be used within the device. So you can have a true or complement, that means active low or active high signal that could be there in this device. A GSR input is also provided to allow user registers to be set to a user predefined state. So this global set and reset that is also available so that you can set the device at a user defined state. So these are the global signals that are available at the microcells. Then now one more important block in a this device, that is a fast connect switch matrix. So this fast connect switch matrix that connects signals to the FB inputs. Okay, so here you can see this fast connect uh, switch matrix that connects, okay, these signals to the functional block input. So here you can see all these connections that are from this fast connect switch matrix. Okay, and then it all IOB outputs and all FB outputs that can drive the fast connect matrix. So here you can see that whatever is the functional block outputs as well as whatever are the IOB block outputs. Okay, here you can see these drives this fast connect switch matrix. Any of these that is in outputs of IOB as well as functional block that may be selected through user programming to drive each of this FB within a uniform delay. Then the fast connect switch matrix that is capable of combining multiple internal connections into a single wired AND output before driving the destination FB. This also provides additional logic capability and it increases the effective logic fan-in of the destination FB. That means whatever are the number of inputs that you can apply to the gates in this FB that are increased because of this logic capability. And also this is available for internal connections which are originating from FB outputs only, and it is automatically invoked by the development software where it is available. So here you can connect all these inputs of this fast switch matrix to the, as I said, to the functional block. Then whatever is the output of this functional block, that as well as output of this functional block that is given as an input to this IO block. So this IO block output that drives this fast connect switch matrix. Okay. So this is the fast connect switch matrix of this XC9500 device family. Okay. Then now let us coming to one more block in this family, that is the IO block. So this IO block that interfaces between the internal logic and the device user IO pins. Okay, so whatever is the devices input pins and output pins that are interfaced using this IO block, as well as whatever again the internal logic that is present. So that is also connected using this IO block. So each IO block that includes input buffer, then output driver, output enable selection multiplexer, and user programmable ground control. Okay, so you can see this in this diagram. Okay, so here this is a IO block of this XC9500 family. Okay, so here it has a, as I said, it has a buffer. Okay, so then it has here, this is the buffer, then it has output driver, then output enable selection multiplexer. Here you can see output enable selection multiplexer that is available, then user programmable ground control, and uh, so these are available here. You can see slew rate control mechanism that is also available here. So for that circuitry is also available, and then pull up registers that are also present in this in a IO block. Okay. Now what is the requirement of this pull up register? It is used to prevent floating pins during programming, okay, and other times. So they are disabled during normal operations or normal conditions. Otherwise, uh, these are connected to prevent a floating pins. Okay, so that is the one use of this floating pull-up registers. Then this input buffer which is present in the IO block that is compatible with a standard 5 volt CMOS, then 5 volt TTL, and 3.3 volt signals. Okay, so this is compatible with all these logic levels. Okay, then this input buffer that uses internal 5 volt voltage supply. So here you can see this is connected, this buffer is connected to internal VCC, there is a VCC INT which is of a 5 volt supply, and uh, because of that it ensures that input thresholds that are constant and they do not vary with the input voltage or output voltage. So with this voltages it will not vary, but it will, this thresholds will remain constant at a certain logic level only, because it is directly connected to the internal 5 volt supply. Okay. So this XE9500 devices that are programmed in a system via a standard 4-pin JTAG protocol. So here, as I said earlier, that this devices that uses a in-system programming, and for that 4-pin JTAG protocol, sorry, that is used. Okay, in-system programming that offers quick and efficient design iterations, and it eliminates package handling. So that is the advantage of the in-system programming. As I earlier said, that because we are programming device whenever it is in its chip only. Okay, so that means on its board only. So because of that, handling is not required, and so that is the advantage. So the Xilinx development system that provides the programming data sequence using a Xilinx download cable, and a third party JTAG development system, then JTAG compatibility, board tester, or a simple microprocessor interface that emulates the that means that matches the JTAG instruction sequence. So here all are the that facility that is provided so that we can program. So if we are doing it in a with this board, then actually Xilinx gives a download cable with the development board. Okay, so with a Spartan 3, Xilinx Spartan 3E and all other packages. So that gives a download cable, then a third party JTAG development system. So all these facilities that are provided so that you can easily program this. Okay, so this XE9500 uh, devices that incorporate advanced data security features which fully protect the programming data against unauthorized reading or uh, any unauthorized erasure or reprogramming. So that feature is available of the data security in a XE9500. So that means uh, no one can unauthorizedly read or whatever erase the programming, or no one can reprogram the device. Okay, then the read security bits that can be set up by the user to prevent the internal programming pattern from being read or copied. So there are certain read security bits that user can set so that these patterns cannot be read or copied. When set, they also inhibit further program operations but allow device erasure. Erasing the entire device is the only way to reset the read security bit. The write security bits that provides added protection against accidental device erasure or reprogramming when the JTAG pins are subject to noise, such as during system power up. And but once set, the write protection may be deactivated when the device needs to be reprogrammed with the valid pattern. So these are the XE9500 product family. So here you can see these are the different ICs that are present in this family. So 9536, then 9572, 95108, 95144, 95216 and 95288. So these are the different devices that are available in the XE9500 family. So then actually it is a 95 series where this 36 or this two digits that represents number of macro cells that are present in that device. Okay, so here you can see in this device there are 9536 there are 36 macro cells, in the 9572 there are 72 macro cells, 95108 108, then 95144, in that 144 macro cells, in 95216 there are 216 macro cells, and in the 95288 288 macro cells are present. So depending on the number of macro cells present, usable gates number that also varies. So as I said earlier, in this 95006 product family, there are near about 800 to 6400 usable gates are available. So in a 9536 there are 800 usable gates, while in a 95288 there are 6500 gates are. Okay, and pin to pin delay, that is in a 9536 it is a 5 nanosecond, while in a 95288 it is a 10 nanoseconds. Okay, as now as the number of gates that increases, number of macro cells that are increasing, and because of that delay also increases. So as the size of your circuitry that is a big, delay will also get increased. So that is the one disadvantage, but otherwise you are getting this much flexibility for the programming here because it has 288 macro cells that are available. Then registers, so those many registers will be available depending on how many macro cells are available. So जेवढ्या macro cells असतील तेवढेच त्याच्यामध्ये registers पण available असतील. Okay, so maximum IO pins that are available, that are also present here, and then this is the packages, in which package these pins are, these products are available, that is listed over here. Okay, so this is about the XC9500 product family. Okay, so now if we go for the advantages of this CPLDs, then we can say that CPLDs that can realize a complex designs. Okay, so for example, we can uh, design graphics controller, then LAN controller, UARTs, then cache control, and many other functions that you can design using this CPLD. A significant advantage of CPLD is that they provide simple design that changes through reprogramming, that you can change through reprogramming. So all commercial CPLDs products are reprogrammable. So remember that every CPLD product that is available, that you can reprogram. So that means once you reprogram, but you can erase that program and then again you can have another programming. Predictability of circuit implementation is one of the strongest advantage of CPLD architecture, as the designs often partition naturally into the SPLD like blocks in a CPLD. So there are SPLD like blocks are there. So you can predict for whatever is the circuit implementation, whether it is going to be correct one or not, that you can predict. And then as it has a higher speed of operation, so that is again advantage of this CPLD. Okay, so this is about IC, that is a XC9500 device family, which is developed by Xilinx. Okay, so again, here there may be question in examination on what are right architecture of this device. Okay, so XC9500. So you need to draw the neat diagram of this architecture, and then you need to explain all these functional blocks. Okay, so all these blocks which are present in that device. So if you have any doubt about this, you may ask. We have still 5 minutes. Any doubt?
No, ma'am.
So actually this is a theoretical part only. Okay, so here all these details that you will be available in a data sheet of all these ICs. Okay, so you can refer all these data sheets for XC9500 series as well as Max 7000 series. Okay, whenever we are going for revision of this unit again, so that time again we will discuss about these ICs. Okay, so for today we will stop here. If you have any query, you can ask. Also, as I said earlier, on Friday we will have one test on fifth unit, that is uh, testing of logic devices, logic circuits. Okay, so that we will have there on Friday at 3 to 4 p.m. Okay, so now today you may leave this meeting. Thank you.